Good afternoon. My name is Vehide. I'm Associate Dean for Research and Innovation in the College of Engineering. It's my pleasure to welcome you to the second seminar in our Faculty Research Seminar Series this fall. Our second speaker in the series is Dr. Rory Roberts, Associate Professor, Mechanical Engineering. He joined us from Wright State University just this fall, and he's been quite busy already. He is working in an area which is quite at the state of the art and of high demand, and that is in fuel cell systems research, particularly higher temperature solid oxide fuel cell. Of course, he has done work in many other areas. He received his Ph.D. in mechanical engineering from University of California, Irvine. He worked at Rolls-Royce for a few years, and then he joined Wright State in 2009, and he joined us in 2020. He has worked in, as I said, many other areas as well, but I want to give him the time during this presentation not to talk about just his research in the current area, but perhaps he will touch on some other areas as well that he has worked on. And I will turn it over to him. And again, thank you for attending.
So thank you for the introduction. Again, my name is Rory Roberts, and today I'll be kind of giving you an overview of some of my research and some of the areas I've worked in. So it's, in a way, it kind of, there's a lot of different areas I've worked in, but one of the underlying themes, I guess, of my research is design and optimization of multidisciplinary systems. And that's kind of where I'll start off today, kind of talking about that, and then branch off into some other areas of research. So kind of the outline of my talk today is going to be the motivation of my research, kind of the overall view of the general research approach, and specific areas of research that I'm working on that I've branched out into with kind of this underlying design and optimization of, I would say, more complex and integrated systems. And so a lot of the motivation, and I would say opportunity out there working in research, is looking at the system integration design. And today, a lot of the systems that we are developing are getting much, much more complex and are pushing the cutting edge that requires a really better understanding in the conceptual design for higher integration. Some example of these would be any kind of aircraft, vehicle, some of these really complex systems that take years to develop. And traditionally, system integration and design is a steady state driven process during the conceptual design. And what is needed is the understanding of the transient behavior during the conceptual design process to ensure you can get the desired operation of the system you want. And so, for example, I have here for like an aircraft is for, you look at a design space, and typically I would look at an altitude and a speed and say the design space is basically what you see inside the dotted line, but we will evaluate and design at point A. That will be our design point, and we assess and design our system based on that. And for good merit, to make sure that we can operate, for example, a takeoff, cruise, and maybe a lower cruise or descent, we would look at another operating conditions of B and C, but we would do that typically in a traditional way would be a steady state approach. And so we would evaluate, making sure that we are hitting what would be our desired performance at those cases. But what we lack during a conceptual phase is how do we transition from point B to point A? Assuming when we take off and we go into a cruise, for example, how do we transition to that? And once we develop the system, we start testing it, then we get more information, and a lot of times it can cause program delays and redesigns. But if you can bring as much information forward in the design process in the conceptual phase, the better off you will be in having to make significant changes. Because as your design, the further along you get along your design process, the less flexibility that you have in altering your design. It's also the more information you have, and unfortunately you have less flexibility. And so not knowing this path, essentially, how you transition and typically a transient way from one operating point to the other can be very valuable. To give you an example, some of the latest tactical fighters took 25 years or so to develop. And you're starting to get to the career of one engineer. And so if you want to really go out and design more complex, more vehicles out there, we can't get to where we're designing across 2 careers of engineers just to develop the system. So a new process needs to be developed, or at least a methodology in the sense of how you capture this transient behavior. So one of the downfalls is it's easy to say, okay, we'll include transient analysis in the conceptual design phase. We'll do a bunch of trade studies or conceptual design studies of transient systems. Unfortunately, that's not as straightforward as just doing a steady state analysis, because once you do that, it requires you to develop a control system, which is actually a part of your system. So it's another component, another subsystem that essentially is guiding and controlling your system based on how you want it to behave and operate. This control system is specific to any particular system architecture and component sizes. So as I look at different component sizing and maybe even some topology or architecture, that control system will change. And so you can't use the same control system for each design iteration you're evaluating. And you may want to iterate thousands of designs potentially. Therefore, the control system must be developed for every dynamic system analyzed. And even if you were able to do that, it's also could be subjective and can mislead the design. For example, I may have system A and system B. They're slightly different, and I want to evaluate based on some kind of cost function or performance metric, which is better. And I may develop a control system from one for A and a control system for B to evaluate them and compare apples to apples. But unfortunately, I may have done a poor control system for system B, and B may actually be the best system, but because my control system was poorly designed, it actually came out not the best system, and you end up picking A. So with this, the transient analysis needed during the conceptual design process, and this will require the control system to either be eliminated from the process or automatically generated as part of the process. So the objective is to enable design of complex multidisciplinary systems with optimal performance, behavior, and response time. So not just performance, we're also looking at behavior and desired response time. So we look at developing a design methodology capable of evaluating and predicting, comparing, and simulating these system architectures in a very rapid way so that we, in a timely manner during the conceptual design phase. And apply this design methodology and tools to specific applications. And so this is essentially the research base. And so looking at system level analysis for design, including control. This is also known as co-design. Many researchers out there have looked at ways to do co-design for system topology, component sizing, and control subsystems. So they're essentially, what you're doing is you're integrating optimal control with design optimization, and so that you're combining really steady state and dynamic modeling in a sense. And so that requires controls experts as well as design system experts. So design optimization essentially starts including optimal control approaches. And basically, kind of to back out, some of this work branched off into other focus areas where we developed some design tools, some tip-to-tail aircraft modeling I'll show, and then some solid oxide fuel cell research that I'll show you as well. Also including some thermal management systems and some high-energy laser systems. Feel free if you have any questions. I didn't say this before, but if you do have any questions, feel free to ask me at any time. So, looking at the design process of the transient system, you know, the typical design process, you have your conceptual design, preliminary design, and then your detailed design. And sometimes this is labeled and there's different terminology, but this kind of shows the flow of how you would develop a system. You have a system objectives and constraints. You would have, if you want to use modeling aided design, use some tools, you would use some low fidelity component models. You'd have like a library of component models that help do your analysis. You start looking at system architectures or topologies. Then you would go into the conceptual design optimization, looking at what all the sizes are, what is the topology or architecture that meets your criteria, and which is the best that either minimizes your cost function or your cost or your objective, or maximizes your objective. Then you go into preliminary. I put this step here as a kind of preliminary design model generation. It'd be nice if you had some more of an automated way of taking a conceptual design tool and automatically transition it to more higher fidelity preliminary design tool. And typically in design process, this is where you would start introducing some controls. And it shows here kind of the dotted line. That would be some controls communication. So it wouldn't be until you got to the preliminary design phase that you would start looking at the control system. And your detailed design phase is where you've actually really solidified the design, you're putting it out for production or final testing. Preliminary design, you're doing some testing and such. So some of the work I've done in the past, couple years ago, I worked with Air Force and a small company, PC Krause and Associates. And our challenge is design process is how can you evaluate, let's say, millions of system concepts at once, or not once, but very quickly, even infeasible. And the idea here is, the best way I could describe it is, if I had a bag of Legos and I had all these different Legos in here in this bag, and I had a system, I wanted to build a system with certain objectives and constraints. What are all the configurations or the ways that I can construct those Legos in the bag? And some of them are going to be infeasible for what I want. But how do I look at all possible combinations and evaluate that and determine what's infeasible, what's feasible, and what would be the best system move forward based on the architecture and topology? So in doing this, as you can imagine, the amount of different possibilities and architectures can be very, very large. For example, if I had 14 components, that has 25 possible different combination connections, and it ends up getting to, basically, I have over 33 million architectures that could be put together by these 14 components, and only 120 of them are validated. So what's a process in which we could look at all these? In a sense, what you're doing is trying to replace some of the experience, not replace, but aid a design engineer in a system with looking at basic system architectures you didn't realize that exist. Because typically it's the experience of system engineers and experts that guide you through this process and look at a limited set of the design space. But if there's 33 million different architectures just with 14 components, we could do a brute force of this where we're just kind of evaluating one by one. And this takes 900 seconds to evaluate to see what's infeasible and what is feasible. And then it'll take even further to go find out to evaluate them. So using schema theory to identify was used to identify invalid architectures, and this sped it up till we were able to do it in like 0.27 seconds. And so this was a tool called Parse that was developed, and it also did some conceptual design optimization as well. And Parse stood for Propulsion Architecture, Rapid Synthesis, and Evaluation. So this was a tool that gave us 3,000 times speed up in evaluating these potential architectures, and we did some studies. Another part of a tool we looked at was what we call trades, looking at the transient design optimization of systems. So this is more looking at the optimal control, essentially, and how to evaluate a system. You can go out and develop a dynamic model of a system versus a steady state model, but then you have to develop the controls as I described before. And that becomes, can become very cumbersome as you're trying to really explore this design space. So what we did was we came up with this tool, with an approach, I should say, and built a tool around it, where we take in user-defined input, system architecture. In this case, we're not generating architectures, we're rapidly evaluating architecture. So the user provides the architecture, user provides the initial component sizing, and maybe some time dependent boundary conditions, which we would call mission profiles or loads, and then any constraints like temperature constraints and such. And then we would perform the system analysis and output the optimal, and essentially the output would be the optimal time dependent path. And this was implemented in Simulink and MATLAB. And it wasn't really your traditional way of doing Simulink, because we actually just used Simulink just to kind of show how we could set this up, and maybe you could do this in a Python or some other open source. But if you use Simulink, in this case, it's just used mainly for a graphical interface. So we put together these component models, and you would build this architecture. So the user would define the architecture by connecting these, let's say, Legos again, or components, and then you'd be able to set some sizing and some initial conditions with some of these components, and with that you can use the code that would automatically generate all the conservation equations, conservation mass and energy for this system. So there was essentially a set of components that were developed that had the governing equations attached with each one. And then with these components, you could do some fluid analysis. And these are dynamic models. And you could do this and put it together and essentially set up a cost function for optimization in the time dependent, in the time domain, or more of a temporal approach, so that you didn't have to develop the controls, and it would pick the optimal path based on your cost function. So what we did was a first order Taylor series approximation of a derivative here, was so that we turned this in from an ODE to more of an algebraic equation. So not to kind of bore you with all the equations here, but essentially here's the conservation of energy for a tank. So the energy in, energy out. We have various terms for the energy stored, the Q dot in, and the loss to surroundings and the flow in and out. And so with that, we're able to construct a system of equations, and this is an example of a tank. So every one of those models has this type of conservation equations for mass and energy. And then we would go through and do what we would create the connectivity matrix. So when the user would put in connect block 1, block 2, and 3, and 4, this would represent a matrix on how these were connected, and we were able to take that and then determine how the equations were then connected to create your system equations and do the evaluation. So for example, block 1 here goes into block 2, so there's a 1 here. And you can see how that creates that connectivity matrix. And this is all done in the background within the code. So once you have this developed, the users is essentially able to establish a cost function and to connect this architecture and then run the system. And what you're essentially doing is you have a current operating point. This would be your initial condition. And then with each time step, you're determining what is your optimal next operating point. And this is essentially determining what your control path should be, what your control inputs should be to the system. And so if you ever develop a controller, this is the path you would want to follow. It would be the optimal control path. So first, we build a system, we build a tank, heat source, so we have essentially have mass flow. In this case, mass flow will be our controlled parameter. And what we have here is we have heat source 1, heat source 2, and heat source 3. We have various heat loads occurring in these heat, or let's call these maybe electronics, as they're turning on and off. We need to maintain a temperature. And so we have a cold water tank, and we can flow fluid through heat source 1 and split it accordingly here. It'll merge back together and go into tank 2. And to show a sample of this, what we have here is we have some constraints. Temperature 2 is the heat source here in blue. We want it below or equal to 315 Kelvin. And temperature 4 here is the heat source here at 4. It's in the red. We want it below or equal to 350. And temperature 5 here in the yellow, as we want it below or equal to 325. And what we're doing is we're actually, our boundary conditions, or our time-dependent boundary conditions or profiles, is these heat inputs into these heat sources. So imagine it's like the heat generated in some electronic sources. And so what we can control, or we have the ability to control, is the mass flow of fluid going through these to maintain these temperatures. And if you use this type of tool, you're able to essentially maintain these temperature constraints. We stopped here at 350. We maintain here at 325, and here we just almost got to 315 and drop. As you can see, we have sinusoidal inputs of heat, as well as a heat pulse. This is kind of an extreme heat pulse happening here at heat source 2. And this is the resulting optimal mass flow that will be required in order to maintain these temperatures in the system. So if I were to take these results, what I would want to do is have my control system, if this was an acceptable system design, my control system would want to mimic or essentially have these same mass flows, so that I am, in a sense, in this case, the cost function was minimize mass flow needed. So that's why we was able to hit constraints. I forgot to mention that before. But we're able to hit these temperature constraints while minimizing mass flow. And we could keep them colder by increasing the mass flow higher, but we don't want to do that. We don't want to waste cooling capacity. So this provides your optimal mass flows in order to maintain your constraints and minimize your flow rates. Now, if I wanted to add some valve dynamics, here's a similar simulation with some heat sources being sinusoidal with different frequencies and magnitudes, with a heat pulse with the same type of heat source or architecture. And we have some of the same constraints here with the temperature response. And here's the mass flows that the system is essentially solving for the optimal path in order to barely maintain our mid constraints. We can also go in and add the ideal valve response. So we can add some valve dynamics. In this case, we had a half-a-second time constant. So when you're operating this valve to supply flow here and to split it here, there'll be a valve right at 2 and a valve pretty much here. I don't have them labeled there. It would take almost 2 seconds for it to hit that valve to reach its steady state opening point. And so that does change the dynamics of mass flow. So you can see that we're still able to maintain the constraints of the temperatures, but it's not as a smooth of curves you had that you would see kind of the heat source. There is those other dynamics occurring because of the valve dynamics. So you can add other dynamics to the system and some real actuator responses and then predict what your optimal control path is. So from here, I'll transition to kind of the next preliminary design tool that we've done some work in. And again, this is kind of transitioning back more towards some of the general, from the general research approaches I've done to now getting the more specific. You can do more preliminary design with Simulink type modeling framework. I put this one here because we've worked with open source Modelica. This is called Open Modelica in Dakota, to do some dynamic modeling of complex systems. I kind of had this slide out of order. I probably should put it afterwards, but this is an open source software that we've taught a short course on. It's a very powerful piece of software that you can do multidisciplinary system modeling. And so I kind of thought there is something that's very, very useful. Of course, with being open source, it's hard to find support for it as much as you wish. But one powerful thing about this tool is it's acausal. And what I mean by acausal, what I showed you before, even the tool I showed you before, you're assuming a direction of flow. You're assuming flow is always going in one direction, and you develop your equations appropriately. So you know what the enthalpy out of one component is, and the enthalpy in of one component source, the flow coming in. This tool is able to handle, that's called causal, I've picked the direction. This tool, Modelica, is able to handle acausal. So I could actually have reverse flows, and this typically can happen in a refrigeration system. So it's a very powerful tool in the sense that allows you to solve systems and have it within an acausal way. We have a background of doing some work in what we call tip-to-tail modeling. And what I mean by tip-to-tail modeling is a way of modeling the entire aircraft, or at least how we see the entire aircraft. And this was mainly motivated by power and thermal management, essentially looking at the energy-optimized aircraft. And that's where we coined the tip-to-tail. You're including, from the tip to the tail of the aircraft. Typically, if you do a model for an aircraft, if you think of a simulator, a pilot would be flying a simulator of an aircraft, and that model would include the physics and the equations of motion, conservation equations for flight. So this would be a 60 degree of freedom for the aircraft, and all the drag forces, the actuator responses, and even some models for the propulsion system, so you can predict thrust and reaction of the vehicle for the pilot to have a very real, accurate flying of a virtual plane. What we're talking about here is including that and all the internal systems. So not only do you include what we call the air vehicle, that's all the 6 degrees of freedom model with all the aerodynamics and flight control areas, actuators and such, but also includes the engine, which can be included with the other example. This includes the engine model. Also, what you see here is this is the engine model. There's also this very complex thermal management system and fuel system within an aircraft, especially military aircraft, because your fuel ends up becoming the blood of your aircraft in a sense, because it's what's utilized to cool your hydraulic fluids, your generator, your electronics, your controllers, and then it's also used to help cool some of your cockpit and some of your avionics, which is a lot of your controllers. So what this represents is a very complex model of the aircraft, and this is a dynamic model. So not only are you flying an aircraft virtually, but you know exactly what are a lot of the temperatures and pressures throughout the aircraft. And this was developed so that we have a better understanding of thermal management within the aircraft. So I'll transition from the tip-to-tail modeling work to some specific areas of research that we've been active in. Adaptive engine, hypersonic vehicles, solid oxide fuel cells, as was mentioned, and some advanced thermal management and some green aviation. The variable cycle engine architecture is something that's being developed right now by GE. Your typical aircraft engine is a two-stream engine. And what I mean by two-stream engine is typically you have airflow coming in, and this is a three-stream engine, but typically you have just one stream here. Air can go through around the core. When I say the core, that's where this combustor is, and that would be the inner stream. And so your commercial aircraft that you would fly, like I said, Boeing 737 or such, would be a two-stream engine with a very high bypass ratio. And what I mean by bypass ratio is you're sending a lot of air around this core in this bypass stream. So that's why you see this very big diameter engine on the wing of the aircraft that you're boarding, because you want to essentially get the high bypass ratio for efficiency. For like a tactical aircraft that wants supersonic, above Mach 1 and even up to maybe Mach 2 or higher, you want a low bypass ratio, since most of your flow will go through this core, giving you a high speed flow so that you can take the aircraft at higher speeds. So it's kind of like having your sports car. it's not going to be very efficient, but you're going to have a lot of performance. In the high bypass in the commercial, you're not going to go as fast, but you'll have a high efficiency. So what the adaptive engine does here is it basically provides a third stream, a third wave of your flow going. And what it allows you to do to have the best of both worlds. You can actually manipulate these nozzles here and modulate how much flow is going in the inner cores versus the outside stream. So when I want a high efficiency flight, I can cruise and have a high bypass. When I really want to take off and go faster, I can close this down, have a lot more flow going through the core, and have a high performance, high speed aircraft all at the same time. The problem is this is a very complex engine with lots of moving parts. You essentially have all these variable geometry features, and it's a very highly coupled engine. As you actuate any of these components, it redistributes the flow and changes the operation of the engine very rapidly. So it's a very dynamic and highly integrated system. So we've done modeling work with the support of CITMAV, which is the Center of Integrated Thermal Management Air Vehicles that was sponsored by Air Force and several aerospace industry to understand this engine and develop and use it for some of our aircraft models. Also, now looking at the solid oxide fuel cell research, a lot of our solid oxide fuel cell research is focused on pressurized operation, and this is typically for high power density. If you want a high power density fuel cell, one of the ways is to pressurize the system, almost like supercharging it, to get a high power density electrical power production. Plus, if you want to go in aerospace, if you're going up at higher altitudes, you don't want to, you're going to have lower pressure, so you need to pressurize the fuel cell as well, so that you have a good amount of reactants. You'd be operating at a high altitude would be closer to operating almost like a vacuum. When you get to like 35,000 feet, you're only looking at about 15 to 20% of your atmosphere. So some of the work we have is in high-speed aircraft in power and thermal management. In 2020, the DoD stated it wants to concentrate its critical technologies and research on technologies such as hypersonic vehicles and weapons, directed energy, and autonomous systems. So this is one of the focus for the Department of Defense. And so this kind of lines up with a lot of the research funding, which is one of its highest this year. Also for electric aircraft and propulsion, solid oxide fuel cell can be a good candidate for that, because NASA and the Department of Energy through RPE have focused on this for the future of, I would say, green aviation. So looking at the thermal and power management system for high-speed aircraft, where the fuel cell, a solid fuel cell becomes ideal. When you have a high-speed vehicle, you don't have a gas turbine engine anymore. So you have to find some way to produce heat, or not, sorry, produce heat. You got plenty of heat. You need to find some way to produce power. So we've looked at the solid oxide fuel cell as a way of producing power, because on this vehicle, everything is hot because you're going at such high speeds. There's a lot of aerodynamic heating. And where I kind of show here in this area where we would scoop air in here, scoop like right here in the aircraft, where we scoop that in, we're looking at about 1,000 degrees C, over 1,000 degrees C air coming in. And we look at fueling this aircraft. And so in this case, that air can be cooled a little bit while heating the fuel and fed directly to a solid oxide fuel cell. Since a solid oxide fuel cell operates at these temperatures anyway. So between 800 to 1,000 degrees C is a very good operating temperature. So it has a nice fit in this case for hypersonic vehicle application. This is some examples of some of the testing or apparatus we put together for doing pressurized solid oxide fuel operation. As you see here, is we have some SOFC tubes that we are feeding. Sorry, I'm getting a phone call. Tubes feeding into the in this chamber. And what this does is allow us to test these SOFC technology at a higher pressure. I just kind of put this up for an example. We do have this actual equipment where we have the solid oxide fuel cell. You can't see because it's behind this, but this is where the solid oxide fuel cell's pictured. And this is the chamber that we're able to put in and test it and emulate it at high temperature and high pressure conditions that you would have during flight. Looking at commercial green aviation, NASA's 2025 targets, and I probably should have updated this because this is when it originally came out. 2025 is just around the corner, it seems like. Probably more 10 years out now. But their targets for commercial aviation is to reduce noise by 72 dB. That's a typo, so it would be a small d there, decibels. And also reduce NOx emissions by 75% and reduce fuel burn by 75%. So they want lower noise for urban travel and airports in cities, also with lower emissions and more cost-effective, lower impact to the environment by reducing fuel burn, and be able to utilize this in existing airports, this aircraft. So that's their target for the aviation, and they have concepts they've been looking for. Another desire is for carbon-free and carbon-neutral aviation. And one of the things they identified, if you want for efficient aviation and reduce noise, is how do you increase the propulsion efficiency? And the engine I spoke about before, one of the ways to do it is to increase the bypass ratio. Essentially, I want as much airflow moving through the engine as I can. It's much more efficient to move a higher volume of air from a propulsion standpoint versus having a smaller volume of air going faster. If you look at exergy, that's one way to support it, because if I exhaust something at a very high temperature, high velocity environment, there is essentially a lot of available work and energy in that flow that I'm essentially destroying exergy in the process. So for high efficiency, what I want is the air to be at a temperature just a little bit higher than the atmospheric temperature exiting my propulsion system, and at a velocity just a little bit faster than what I need for propulsion. So that drives you to the higher bypass ratio. And the other way is to reduce drag on the aircraft. And so one of the concepts that has been put out for NASA is distributed electric propulsion. So, if I were to increase the bypass ratio of a commercial engine without distributed propulsion, that engine you see on the wing of your aircraft essentially would be as big as the fuselage, and to the point where the wing would be dragging the tarmac. So you can only get it so big. But if you do distributed propulsion, essentially you have a bunch of fans here. These are not gas turbine engines. These are cold air. You have a bunch of fans in the back of the aircraft that are providing propulsion, essentially giving you this high bypass ratio, and also reducing the noise. So you get a high effective bypass ratio, and you reduce the noise by having it above the body here on this aircraft. Another thing is there's also a benefit from boundary layer ingestion. You have a boundary layer coming here, and you're exhausting it out the back. So you have less drag here on the exit of the aircraft. So this concept of distributed propulsion provides high bypass ratio and reduced drag, ultimately increasing your efficiency of your aircraft. The issue is, though, you're talking about electric propulsion. Typically we have gas turbine engines. Producing electricity on the aircraft in a very high power density and efficient manner is another challenge, because you need to have high efficiencies and you need to be able to distribute this electricity around the aircraft. We're talking 30 to 60 megawatts of power, and there could be a substantial amount of, let's say, just distribution cables of copper if you do it in traditional ways. And also, these electric motors have to be high power density electric motors, and the generators have to be high power density. And the turbo, in this case, they show a turbo generator. Basically, you have a gas turbine driving a generator to produce your electricity, and it's powering these electric motors. So all of these are new technologies that need to be developed, from motors, generators, power production, and some of the distribution for the electrical system. So there's a drive by RPE for the Ascend program, Cable program, and REACH program for a carbon neutral electric propulsion power and thermal system. So essentially, Ascend is concentrating on the electric motor and high power density electric motor and thermal management of these electric motors. Cable is a program they're looking for the power distribution within the aircraft, and REACH is a program that they're looking at the power production within the aircraft. With these three combined, you have your total system for your electric propulsion. What they're looking at is a Boeing 737 class aircraft, and they propose as one of the fuels is bioliquefied natural gas as a fuel source. And in this case, it could actually be a thermal battery. Since it's at 112 to 130 Kelvin, depending on what pressure you're storing it at, that provides you the ability to cool some of your components within the aircraft. So, this is a program that we have proposed to, and there's looking at a solid oxide fuel cell with a gas turbine integration to have a high power density and high efficiency system to produce power to drive the electric motors for that distributed propulsion you saw before. And so it also requires high capacities, motors, generators, and power electronics. So this is a green carbon neutral concept by looking at bioliquefied natural gas proposed by RPE. So what is the benefit? How does a solid oxide, what I call a solid oxide fuel cell combustor with a gas turbine versus just a regular turbo generator, how does that compare? How do those two compare? So if I look at the turbo generator that was proposed in that NASA concept versus what was proposed in the previous slide with a solid oxide fuel cell combustor and a gas turbine together, what you're seeing here is how they compare if I were to fly these for multiple hours of flight time, essentially. So what you see here at the beginning, this is the weight of the two systems. The red is a solid oxide fuel cell gas turbine. The blue is the turbo generator. So zero flight, I just have the weight of the systems. As I increase time of flight, I am increasing the amount of fuel that's needed in order to sustain that flight. That's basically how much fuel is consumed by each one of these systems. And so I look at, and I plot this over time, hours of flight. There's a break-even point of about 3 hours to where the solid oxide fuel cell plus its fuel that's needed is equal to the turbo generator. So anything over a three-hour flight would be either technology, doesn't matter, go with the cheapest, lowest maintenance technology. Basically what gives you the best cost per passenger miles. But as you start going in longer flights, you can see here that the overall weight of the solid oxide fuel cell gas turbine is lower. So for longer flights, this technology shows promise. So here I'll transition to another area of research we've been working in. Is more on high energy laser systems. High energy laser systems have some challenges from a thermal management because they are producing large amounts of heat, and these laser diodes also need to be maintained within a plus or minus 2 to 3 degrees Celsius to maintain good operation. And so there's very high heat fluxes that can be turned on and off. So imagine you have zero heat to orders of magnitude change in heat to maybe 10 to 100 watts per centimeter squared of heat being produced. And not only do you have to remove this heat from the laser, you have to do it with a very small delta T, or with very small change in the temperature of the laser system. So what you see here is we've done some multidisciplinary modeling and to help and do some design optimization of a high energy laser. And what you see here is if I was operating my diodes at my nominal temperature, I would get a wavelength here of around 808 nanometers, and I would get a specific power density here, or a spectral power density here. If I allow my temperature to rise on a series of diodes, I start getting less power output, and there's also a phase shift in the actual output wavelength of the laser diodes. So, and this is just a small phase shift. So what we show here on the right is here's the optical power in blue, the laser diode, and initially at 5 seconds we activate it. The power coming out is around, I guess that's around 75,000 watts, but then it starts reducing over time because it's warming up. What you see here is the optical gain medium. This is how much optical power is going through the gain medium. The laser diode is providing power, optical power in, and the laser gain medium is providing a coherent beam coming out. The rest in between these two curves is turned into heat. The reason why you have this drop in efficiency over time is as this wavelength is shifting time, so is your ability to absorb the wavelength within your gain medium. So what happens is as your temperatures change, the system, the issues will propagate down the system, and you will start producing more and more heat. You can get a runaway laser system in this case if you do not cool it properly, and essentially you're producing more heat and it just runs away till, if you don't turn it off, it could burn itself up. Essentially in the pink here is the optical power out. So what we did here was evaluate the thermal management and looking at the optical thermal interaction on how you would design this system and how you would interact with the thermal management system, and what is the best approach for cooling it based on what type of coolant you have, what's the delta T, what is the overall heat transfer, what is the capacitance of the fluid. There's a lot of non-dimensional, and we also looked at the non-dimensional design parameters so that we can essentially find a solution space that you can adapt to your current situation. There's also may be control approaches that changes based on the characteristics of your system and the interaction, the optical thermal interaction. So I probably will end here. I think I'm running out of time. I'm about 50 minutes in, but I'll just go on to questions here and open up for questions if anybody has any.
Thank you so much. Appreciate it. I know you have a lot more material to present, and it's quite interesting. And I think as I was listening, it certainly seems to certain areas certainly very similar to what you're trying to do for vehicle engineering. And you did refer to it as vehicle, and indeed an airplane is also a vehicle. So there's a lot of synergy there, and I hope that we can take advantage of those synergies and your interest and expertise in these areas. So the audience are free to unmute themselves. If you can't, let me know, but you should be able to unmute yourself and turn on your video so that you can ask your question, or raise your hand if you're unable to unmute.
This is Dale. I can't get my video on, but I just want to confirm what Vehide just said about vehicle engineering program. One of the reasons we called it vehicle engineering was because we wanted to have the ability to include the aviation, as well as could potentially be ships and other things of that nature, although we're landlocked, that's more unlikely. But we wanted to be open to any kind of vehicle. So I think that there's great opportunity to find ways to blend some of this kind of activity into the vehicle engineering program.
I agree with that, Rory. So especially, we have so many faculty in ME with expertise in different areas, including noise. You mentioned noise several times in your presentation. So we have expertise in that. We have equipment also. Vibration is another one with Steve Anton, Al Bakri, all of these people working. So anytime you talk to Air Force with your projects or otherwise, if you find an opportunity, let us know. We can collaborate, definitely. We can somehow interject and work on that as well. Okay. So it's going to be going forward. Good synergy in all these areas, in addition to what you do. Okay.
I have a comment. I cannot turn my video on, but that's okay. The thermal management system that you mentioned, how miniaturized can it get?
As in, did you say individualized?
The thermal management system for lasers that you mentioned.
Yeah.
How can you apply it to something like semiconductor chips?
You can do the same. It's I guess it depends on what the motivation is or objective is of the thermal management. With a silicon, it would be for more, you're thinking more of just electronics cooling, and possibly in general, I'm guessing. And so then it's just kind of trying to maintain I would say, a steady heat flux, cooling the chips. In this case, with the laser, it was more challenging in the sense that you were trying to almost like a thermal switch. You would like to keep the diode at a constant temperature while you're essentially having 0 to possibly 20 to 100 watts per centimeter squared of heat flux on it. I don't know if is that going the right direction of your question?
The heat flux in the inside the chip, electronic chip, from what I know, it is so high. Some people compare it to the nuclear power reactor at the core of it. So, I was wondering if you can handle that kind of heat flux to cool it down.
I mean, some of the work I was looking at was getting around the 25 to 100 watts per centimeter squared. So that's potentially, and that's pretty high, but that was doing more of a vaporization, local vaporization. And so if you want to maintain that and essentially you kind of, electronics have done that with ammonia heat pipes and such to try to get that heat flux up by having a phase change at the surface, and then doing some surface modifications in order to increase the heat transfer at the surface as well. I haven't done as much work in optimizing that, but I've looked at more how do I get a system to respond very quickly. So if you had a chip that was responding very quickly, like it was coming on and then going off, that could be like a radar system that you're using intermittently. That could be a laser system. Then there's how do you have more of a thermal switch that you can turn the cooling on and off rapidly.
Okay.
I had this video here, and maybe I should have shown that in the question here, but this is a concept that we're looking to test before, and it's what I call controlled boiling. Essentially what I'm doing here is, I don't know if it'll play, it may not play in this case, is I'm changing the heat transfer capability by manipulating the operating pressure, so that I have CO2 in this chamber, and I'm adding heat. This is a model, but I'm adding heat to it, and I'm able to go in and out of boiling by manipulating the pressure. So if you can have a valve, something maybe like a diesel fuel injector that you could do kind of a pulse width modulation, you can kind of operate the pressure really rapidly, change the pressure so that you can go in and release the pressure going into like a flash boiling, kind of holding it there. And if you change the pressure, you're changing the saturation temperature, and you're changing the speed at which you're manipulating how much you're boiling. So this gives you a double benefit in the heat transfer, because one, you're going from a single phase cooling to a two-phase cooling, and you're also cooling your coolant as well, because I will drop the temperature of that CO2 as well as it starts boiling, because it's going to pull heat from itself. So that the temperature difference will change. And so this is if I was looking at a diode, if I wanted to go from 0 heat transfer to 100 watts per centimeter squared, how can I do that in a millisecond? Actually, I should say milliseconds, not a millisecond, but within less than a second.
Okay, thank you.
You had this, Rory, you had that graph that showed where there would be a crossing between using the solid oxide fuel cell versus current technology gas turbine engines, right? So, yeah, this figure. So, what kind of a specific power or power density are you assuming for the fuel cell? And what is the target, say, in 5 years? Because you were talking about green aviation being 5 to 10 years, 2025, maybe a little bit later now. So, there was also, in automotive, there was target specific power, for example, for fuel cells.
In order for a all-electric propulsion aircraft to make sense, viable economic sense, not looking at the capital expense, but more operational and size and weight, you need to be around 2.25 to 2.5 kilowatts per kilogram for your overall system and power production. You'll also need to be at about efficiency, I'm probably off a couple percent, but I have some papers, and I'll probably be publishing more papers, around 50% efficiency from fuel to electricity. So in order to justify, I believe, going from a typical gas jet engine, or a high bypass, I should say, jet engine, to a more all-electric aircraft, where you have electric propulsion. And this was a comparison looking at what NASA is assuming for a turbo generator. And NASA's assumptions are really, really high pressure ratios, really high operating temperatures, looking at cutting edge, even high power density generators. And I can't remember if this generator was probably around 15 to 20 kilowatts per kilogram just for the generator. Mm-hmm. And to put that in perspective, like state of the art is like 5 right now. Now that's kind of getting, I'm quoting some numbers off the cuff here a little bit, so it could be up, plus or minus a couple of kilowatts there. And there's probably certainly been some people have demonstrated around 10, but what size system or how many, but I would say, I'm just trying to think what Tesla's motors are at, but I think they're getting around somewhere between the 3 to 5 kilowatts per kilogram on their motors. Mm-hmm. Just to kind of put everything in perspective. So in order for this to be a plausible concept, you need a fuel cell that's above 2 to 2.5 kilowatts per kilogram. You need a generator that's above 8 to 10 kilowatts per kilogram just for this SOFC-Combustor concept, gas turbine concept. So For a turbo generator, you probably need a generator that's around 10 to 15 kilowatts per kilogram. But your turbo generator, the turbine part's much smaller.
Yeah. And as we've seen it with automotive application, I would suspect there will be hybrid systems first before you go to all electric, because they will, at cruise altitudes and so on, you may be able to be better off operating your fuel cell, and you may still need the gas turbine propulsion for takeoff, for example. So
yeah, different operation when you're taking off, because that's you got those 2 pinch points. You got takeoff at high power, but then when you go to high altitude, depending on what technology you pick, you're operating at a low pressure. And so you really lose a lot of power capacity in your gas turbine engine as well. That's a challenge for some aircraft that are becoming almost electrically starved in a way, because they can only pull so much power off the engine when they get to high altitudes.
it'll be fascinating times ahead. So are there any other questions? We're just about 2 or 3 minutes past our end time. So I will stop recording and thank our speaker, Dr. Rory Roberts, for a very interesting talk, and thank you all for attending. And we will leave the Zoom open for a couple more minutes if anyone wants to have a discussion. But thank you all for attending.